In this video, we are going to dive deep into the world of Bluetooth Low Energy advertising. If you don't know a lot about advertising, then stick around because we are going to cover it in a lot of detail. Advertising is very important in Bluetooth Low Energy because it is used by all devices for discovery. We are going to go through exercises. We're going to use Bluetooth sniffers in order to capture the packets and learn everything about Bluetooth Low Energy advertising. You'll probably find this to be very long. It's going to be a long video, but the resources, the topics covered in this video will go into detail that you probably won't find online anywhere, except for the Bluetooth specification itself. So let's dive in. All right, we don't have any time to waste, let's get to it. So this is going to be an advertising, Bluetooth Low Energy advertising masterclass with a focus on legacy advertising in part 1. Part 2, we'll get into extended and go into periodic advertising and then periodic advertising with responses. If you don't understand or know about any of these concepts, don't worry. We are going to cover things all the way from the basics and from scratch. So what we're going to cover in this masterclass is we'll start with some background information about Bluetooth Low Energy and Bluetooth advertising. We'll go into just what advertising means and what it entails for different devices, for Bluetooth Low Energy devices. Then we'll get into advertising and scanning and the different parameters that are used on both ends. Finally, we'll get into the meat of the content, the legacy advertising, and what that means and all the details of that down to the packet level. Now, I won't spend as much time on the theory, and I will get down to the exercises. We'll be using some Silicon Labs development kit to prove and to showcase the different advertising modes and the different advertising types, as well as what you can include in terms of data in your advertising packets. We'll also be using a professional commercial sniffer, a Bluetooth sniffer that we can use to capture over-the-air traffic and take a look at the packets down to the byte level and confirm that our changes on the development kit are actually reflected over the air. So I'm going to be using the Silicon Labs BGM220 Bluetooth Module Explorer kit. And in addition to that, that's going to be the dev kit that we're going to run the exercises on. I will have a GitHub repo that is a companion for this, so it'll have the project that you can run on your own side. I think this Bluetooth Module Explorer kit is just around $15 or $16, so it should be affordable for everyone, and you should be able to get your hands on one, I think, anywhere in the world. So that will be great to get you started and to follow on with this masterclass. In addition to that, I will be using a professional sniffer. My company, NovelBits, is the official distributor for RF Creations, this company that provides this Bluetooth sniffer. Now, it's not cheap. It's in the $20 or above $1,000, so it's not a cheap one. But if you are interested in one in the North America region, whether that's US, Canada, or Mexico, then reach out to me and I will be able to give you a demo and showcase and give you a lot more information about this. And we'll see it in action in this masterclass. You can use any other sniffer as well. This is just as an education tool in this case to actually look at the packets and verify and look at the information that's being sent over the air so we can really understand what advertising means in the context of Bluetooth Low Energy. So just to kind of take a step back, look at the higher level, we're looking at the link layer here in the context of the Bluetooth stack. These are all the levels, all the different layers within a Bluetooth stack, Bluetooth Low Energy stack. We have, starting from the bottom, down to the radio level, we have the physical layer, we have the link layer. On top of that, what's called the HCI or the host controller interface. In some cases, the controller will be on a separate chipset from a host, so they need a standardized interface, which is actually defined in the Bluetooth spec. And this is called the HCI. And that's used to interface and send commands and receive events from the controller level up to the host level. At the host level, we have what's called the L2 cap layer, or logical link control and adaptation protocol. We don't need to worry too much about the details of these, especially for the context of this specific masterclass on advertising. Then we have on top of that Security Manager Attribute Protocol, GATT, which is the Generic Attribute Profile, and we have Generic Access Profile. And on top of that, we have the Apps layer, which is where we will interact with in this masterclass, as well as generally for developing a Bluetooth Low Energy device. So the different components, we'll be interfacing mostly with a gap player, which defines the different roles that we'll talk about for a Bluetooth Low Energy device. This will be provided as a set of APIs by Silicon Labs, for example, in this use case, and allows us to start operations, get events, and interact with the Bluetooth Low Energy stack in order to perform different operations on our device, and in this case, on the development kit from Silicon Labs. The link layer specifically is the most complex part of the system, but understanding it is really crucial. So we'll just dive into it just a little bit and talk about the different states and the state machine in the link layer. So there are multiple states in the link layer. Standby is the idle mode, basically, where the radio is not on or it's not doing anything. There's no data being sent. Nothing is actively being done by the embedded device, by the Bluetooth Low Energy device. Now, we have what's called isochronous broadcasting and synchronization. We won't cover those and we won't talk about those in this masterclass specifically, but we will be focusing on the state of advertising, the state of scanning, and then initiating and connection maybe in a later masterclass. So the focus here is going to be on scanning and advertising. You can have multiple implementations or multiple roles for a specific device. So you can have a device that's advertising and scanning at the same time. They don't really happen at exactly the same time. They actually are round robined or switched by the scheduler, but it can appear to other devices to be happening at the same time. So the two kind of modes, the common modes for a Bluetooth Low Energy device is what's called connectionless communication or connection oriented. Now, in our case, we are going to be focusing on connectionless, or at least staying in that state. Now, we could be still in a connection-oriented configuration, but before we go into the actual connection being established between the two devices, we're still in the similar state as the connectionless. So the two roles here are a broadcaster, or what's called a peripheral when it allows a connection, or an observer, or a scanner, or a Bluetooth Low Energy Central when it allows also and is able to initiate a connection. But basically, for two devices to discover each other, they have to be in basically asymmetric roles. Each one of them will have to be in the advertising state, while the other one has to be in what's called the scanning state. From there on, they can go into what's called a synchronization state that's used for periodic advertising. We won't talk about it in the specific part in the masterclass. Maybe that's for a different session later on. And there's the isochronous broadcasting state, which is used primarily for LE audio. So we'll be focusing on staying in the advertising state and the scanning state. Now, there are different types of advertising that we'll talk about shortly, and that's what allows devices to go into and use what's called the connection-oriented communication or connection-oriented configuration. So that in that case, we'll have a scanning device and an advertising device, but the advertising device is sending out packets that allow a connection from another device. And basically, when the two devices go into this connection state, they'll be able to do more periodic, more persistent communication between the two, bidirectional exchange, and they'll know exactly when to communicate with each other. They can transfer a lot more data between each other. In the connectionless state, usually it's going to be a lot of one-to-many kind of configuration where the advertising device wants many devices to be able to discover it and read the data that it's broadcasting. So when we look at the 2.4 gigahertz spectrum, which is the spectrum, the ISM band, or the industrial, scientific, and medical band that is being utilized by Bluetooth Low Energy, as well as Wi-Fi and other technologies, this is how the spectrum is split up in the context of Bluetooth Low Energy. You have 3 advertising channels. These are called the primary advertising channels, and they're highlighted in the dark blue here. The other ones that are pretty kind of a purple color are called secondary advertising or data channels. So these are more commonly now referred to as general purpose channels because they get used for both during connections and also in what's called extended advertising. Now we are going to be covering only legacy advertising, so the focus will be on these 3 channels that are labeled 37, 38, and 39. And you'll see here that they are placed strategically in the spectrum to avoid the most common Wi-Fi channels, which are 1, 6, and 11. So you'll see that they're spaced apart in a specific manner where they are kind of trying to avoid any of the Wi-Fi, the most common Wi-Fi channels, 1, 6, and 11. And this index here, you'll see it does not go in order. So the 37, 38, and 39 are still labeled that way, even though they are technically, this is channel 0 in terms of the order. This is channel 12, and this is channel 39, still the same, but they are referred to as channel 37, 38, and 39 as the RF channel index and Bluetooth Low Energy. The remaining channels 0 to 36 are what's called the general purpose channels, or the data channels, or secondary advertising channels. Now, if we take a step even further into down into the radio layer, we commonly define what's called the PHY, or the physical layer. In this case, it's really talking about the modulation scheme, the configuration for the radio, and the data rate that's happening by the radio, or the data rate that is used by the radio to send data over the air. So we have different PHYs in Bluetooth Low Energy. We have the 1 meg PHY, which is the standard PHY. This was introduced back in 2010 in the beginning, since Bluetooth Low Energy was introduced in the Bluetooth spec, which was version 4.0. And this is a standard one that's backward compatible with all different Bluetooth Low Energy devices. So you'll see that that's going to be the most commonly used across different BLE devices. We have the 2 meg PHY, which is used for higher speed, higher data rate. This is also supported by many Bluetooth Low Energy devices these days, and even smartphones, but we won't be talking about it very much in this masterclass. We'll be focusing on the 1 meg PHY. Coded PHY is another type of configuration for the radio, and this one focuses on being able to achieve long-range communication, which can actually go kilometers or multiple kilometers only when it's line of sight. However, it can be used in RF congested environments where you can achieve higher reliability. So these are the different PHYs that are available. 2 meg PHY, coded PHY are both optional PHYs that do not have to be implemented in a Bluetooth Low Energy device. The 1 meg PHY is the standard one. And here's a comparison between the different parameters, or the different characteristics of these PHYs. So the 1 mega symbol per second is basically how many symbols represent each bit or each data. And in the case of 1 meg PHY, there is one symbol representing each bit of data that is sent by the device. In the 2 meg PHY, it's 2 mega symbols per second, so one symbol is being sent per bit of data. However, in the case of the coded PHY, it's still using 1 mega symbol per second, but the S here defines how many symbols represent each data bit. So in this case, we have some data redundancy. We have 2 symbols representing each bit. We have 8 symbols representing each bit. That's why the actual data rate will go down, but it will include redundancy, which allows us to do some error correction on the receiver end. We'll get into these in a lot more detail in a different masterclass, but for now, just to understand the differences in the data rate. And then in addition to that, the application level data rate will be varied and will be lower than what the actual data rate of the transmission is. And that's due to some mandatory gaps that need to be in between packets, as well as some overhead from headers and such. So in the case of the 1 meg PHY, really ideally, in a very ideal situation and without any congestion and interference and retransmissions, you can achieve up to 700 kilobits per second, or around that. For 2 meg PHY, it's around 1400 kilobits per second. In all cases, there is error detection built into the protocol, and that's available via the CRC that's computed on the packet, and you can see that. We'll see that when we start looking at packets. Error correction, again, is only available in the coded PHY option, so it's not available for the 1 meg or the 2 meg PHY. In addition, range can be also reduced, will be reduced a little bit for 2 meg PHY just because of the nature of this, and compared to 1 meg PHY, whereas in the coded PHY, the range is obviously going to be increased because of the redundancy of the data and the ability to correct the data and detect errors and correct them on the receiving end. Again, these are optional. The receiver sensitivity, there's some requirements there to go higher in the receiver sensitivity, or go lower on the coded PHY for being able to achieve the longer range. So with Bluetooth Low Energy, there is a unified packet format, and this is what it looks like. It starts with what's called the preamble. In the case of the 1 meg PHY, we have 1 byte. In the case of the 2 meg PHY, we have 2 bytes. And then this is basically a sequence of bits that is used by the receiver in order to detect the start of a packet, so it can synchronize to that and know when to start reading and parsing data. The next 4 bytes are called the access address. For legacy advertising, we'll see that the access address is actually fixed, and it's the same for any advertising packets that are sent using legacy advertising. And that's represented by 4 bytes. In the case of extended, or in the case of connections, that will be different. But in the case of legacy, it is set to a fixed value that's defined in the Bluetooth specification document. Now again, this is all for uncoded PHY. We'll take a look at the coded PHY in the next slide. But for now, the PDU is the protocol data unit. This is what will actually contain the application data that your application will be sending, as well as some header data. So that describes the length and includes some other information so that the receiver can actually parse and be able to know the length of that data so that it can get to the CRC, calculate the CRC then, and then be able to verify the integrity of the packet and request a retransmission in the case of connections. In the case of advertising, if a packet is lost or if it gets corrupted and the CRC is detected to be invalid, then there's nothing really that you can do about that in the advertising, because it's usually in legacy advertising, it's only one directional and there is no communication back and forth between the two devices, between the advertiser and the scanner. We have what's called the constant tone extension, or CTE. This is used in direction finding, so we won't get into this. This is an optional field that's added to the packets when it's used for direction finding, for angle of arrival or angle of departure for location services using Bluetooth Low Energy. In the case of the packet format for coded PHY, it's a little bit different. You'll see there's still a preamble here, though the spec defines these in terms of times, because in terms of the time period that it takes to transmit over the air. However, this is 80 bits. So in this case, because it's also using the 1 mega symbol per second, and it's using 1 symbol per second for the preamble, it's transmitted at 80 bits in this case. So it's 10 bytes versus the 1 or 2 bytes. Access address, then we have what's called the coding indicator, and then there's the term 1 field. These are all necessary in order for the receiver to understand how to parse the second part of that. So you can see here, it's always using the S=8 coding for this part, which gives it a way to read this and know that this is going to be in a fixed format, and it'll be able to parse this coding indicator, which actually indicates whether the next FEC block 2 is configured with configured with S=2 or S=8. So based on the CI field, you'll be able to tell whether it's 2 or 8 and then be able to parse the rest of the data. The PDU here is what will include the actual data, and then we have a CRC and we have some other data included in term 2. We don't need to get into details of this. This will be something that we would look at when we look at coded PHY later on. So advertising and scanning, these two concepts are really crucial in Bluetooth Low Energy. Why do we say that? And that's because it always starts with advertising and scanning. So communication between two devices always starts with one device advertising and one device scanning. So advertising by this device, by a device, will allow another device to scan and discover it. The advertising always starts by sending these advertising packets on one of the 3 primary advertising channels, and then we'll continuously send on each of these channels. So basically, these channels that we looked at here, the 37, 38, and 39, if you look at an advertiser, it will be configured to send an advertising packet on 37, on 38, and 39. Doesn't have to be in that specific order, doesn't have to be on all of them. It can be configured to send on a subset or even just one of these channels, and it can change that order for every time it advertises. Now that means that a scanner will have to continuously scan these 3 specific channels in order to discover the advertising devices. So that's how a scanner will be able to discover that device. Now, if we look at the different parameters, so we talked about this sending a packet on each of the advertising channels. So what happens there, or how does that actually happen? So we go back to a parameter called the advertising interval, which defines the time between the start of two consecutive what's called advertising events. So an advertising event, for example, we say that we advertise at 100 millisecond advertising interval. That means that within that 100 milliseconds, we will have the following happen. We'll have usually, again, and these orders could change. They also could have a limited number of channels being used, and rather than 3, it can be using 2 or 1. But this in general is how most commonly advertising devices will do. What they will do is they will send a packet on 37. The same packet goes on 38, and then the same packet goes on 39. Now this happens, there are requirements in the spec that say that the time from the start of advertising the first one within the event to the advertising of the second one has to be less than or equals to 10 milliseconds. Same for the other one. So you'll see at around maximum, you'll see that maybe 20 milliseconds plus the time it takes to send out this packet. The rest of the time it will actually be asleep, and the radio will not be doing anything for that specific state, for that specific use case. So if we have 100 milliseconds, then 20 plus, say, maybe 5 milliseconds or whatever it takes to advertise this. Say we have around 25 milliseconds used to transmit all that. The rest of that, the 75 milliseconds, the rest of the 100 milliseconds will actually be with the radio being off. So the scanner will have to be scanning on one of these channels and discover this specific packet in order to discover this device. Now the advertising interval has per the spec, can be configured to be down all the way to 20 milliseconds and all the way up to 10,485 plus seconds. In general, you'll see that devices will probably advertise somewhere between 20 milliseconds and go up to maybe a couple of seconds, or maybe 5 or 10 seconds, and not more than that usually. So if we go to the next concept, which is the types of advertising, here we see there's something called ADV-IND, which we'll talk about here shortly. But this is a specific type of advertising. Well, what does that mean? That means that there are general or the specific properties of the advertising that define the type. So we have what's called the general discoverable versus limited discoverable. Now those are not defined at the packet or for the packet type itself, but those are just fields that are included in the advertising data and that can be included optionally. General discoverable means that a device, once it uses that or specifies that in its advertising data, it means that it's just discoverable. There's nothing special about it. The limited discoverable in the spec defines that the scanner should, a recommendation for the scanner to display that as a high priority device. So you can imagine that maybe one device, you tell the user to press a button and you go into a limited time period of using limited discoverable so that the other side, the scanner side, will be able to prioritize that and display it at the top of the list of devices being discovered. So it's really more of a UI thing than it is at the packet level or in terms of restrictions of what it can do or such. The next ones are the most important for distinguishing between advertising types. So we have something called connectable versus non-connectable. Again, this means that a scanner device, or what's called a central device in the case that of a smartphone or some other device that is able to establish a connection with another device, if it sees a connectable advertising packet, it will be able to initiate a connection. If it sees a non-connectable, then the spec prohibits it from establishing or trying to establish a connection. Now, the non-connectable device will not even respond to that anyways, but this defines at the packet level the type that indicates whether it's connectable or non-connectable. Then we have two others, one called scannable versus non-scannable, which we'll talk about here shortly, and then one called directed versus undirected. Scannable means that it can send an additional packet So that happens after sending out the advertising packet. If the device, the scanning device, is in a specific or special mode called the active scanning, it will be able to send what's called a scan request, which allows an advertising device to send a scan response, which is another way, a way for an advertising device to include more data and additional data in that scan response data packet versus just having to send one packet in the advertising channels or in the primary advertising channels. So this allows it to send an additional packet with more data if it needs that capacity. So this is specific and it's defined in the type of the advertising. We have directed versus undirected. In this case, it means that when it's directed, that only a specific device with the address specified in the packet will be able to connect to that device. So this applies only for connectable devices or connectable packets. Undirected is the general, what you'll most commonly see with advertising packets. It'll be the undirected. So the way that this works, the different types, is that it's going to be a combination of these three. So it'll be connectable, scannable, undirected, for example. It can be connectable directed. It can be non-connectable scannable undirected and non-connectable non-scannable undirected. There are specific permutations or combinations that are not available in legacy advertising. So we'll see that here shortly in a specific table that we've gotten from the Bluetooth spec. So going back to the concept of scanning. So on the scanner side, the scanner is the device that wants to discover that advertising device. So it has to, again, tune to the three primary advertising one at a time and do some scanning for a limited time, and then be able to switch to the next one and do scanning again and again until it discovers a packet, at which time it will report that back to the application. The application makes the decision based on the data included in that packet, whether it's the device of interest or not, in order to maybe connect to it or parse the data even. So there are two specific modes of scanning. There's what's called active scanning and passive scanning. Now remember where we said that some advertising packets are scannable versus non-scannable? This is where this comes in. So the scanner can be in the active scanning, in which case if it does see a scannable advertising packet, it will be able to send what's called a scan request packet. So here it'll see, for example, on the right side, you'll see this is a case of active scanning. Device A is the central or the scanner device, and most commonly it's going to be a smartphone. Is going to receive an advertisement from device A, and in that case it found that it is a scannable advertising packet, so it's able to send it what's called a scan request, and in response to that the device will send a scan response. So these will have different data included in the packet most commonly, but it can be the same. It can be used to add additional data where you can't fit all the data in a single advertising packet. In the case of the scanner being in the passive scanning mode, in that case it's just going to receive the advertising packet and it won't scan the scan request, even if the device is sending a scannable advertising packet. So there are a couple of parameters again that define the scanning process, and that's the scan type, which we just talked about, passive versus active, and then we have what's called the scan window and the scan interval, and these go hand in hand. So you have a scanning device. Maybe you define the scan window to be 50 milliseconds with a scanning interval be 100 milliseconds. That means that every 100 milliseconds it's going to wake up and do scanning, active scanning, or passive scanning for 50 milliseconds and then go back to sleep in order to wake up later at the next scanning interval and start the scanning process again. So in this case, if we say 50 and 50 out of 100, it's a 50% duty cycle. This will allow the device to do other things in the middle here. So for example, it can be scanning, but also advertising at the same time. So that it will allow it to advertise and scan. So that has to be coordinated between the different states within the specific LE Bluetooth Low Energy controller. So here's a table taken from the Bluetooth spec, and this defines the different advertising PDU types. So this is the types that we talked about before, and we characterize them by being connectable versus non-connectable, scannable versus non-scannable, and undirected versus directed. And you can see that here. So the legacy advertising PDUs are defined as follows. There's the ADV IND, ADV direct IND, ADV non-connect IND, and ADV scan IND. So these are legacy advertising PDUs, and they are listed here in the table. And this will tell you what is allowed. We can ignore the AUX parts in here because these are for extended advertising, which we're not discussing now. So anything with AUX and EXT is going to be extended advertising, so we can ignore that. Let's focus on the ones that are part of the legacy. So in the legacy, the first one is ADV IND. This is a connectable and scannable, and it's undirected. So it means it's scannable, and that means it does allow a scan request, and it's connectable, so it does allow a connection indication, or similar, what used to be called a connection request packet. Next one we have is connectable directed event. So in this case, it is non-scannable. The directed is always connectable, and in this case, it's called ADV direct IND. Again, does not allow a scan request, but it does allow a connection indication. The next one in the list is non-connect IND. So if we look at that here, it is a non-connectable, non-scannable, undirected event. So in this case, it's not going to be scannable, it's not going to be connectable, and the only thing that it will include is just data that's being advertised in a packet with no type of interaction from the scanning device. The next one on the list is ADV scan IND, and this one is going to be a scannable undirected event. So this is non-connectable. You can see here, you can verify that here. It does not accept what's called a connection indication. So this is the non-connectable scannable undirected event. And in this case, it's called ADV scan IND. So it's similar to this one right here, ADV non-connect IND, with the exception that it does allow a scan request. In terms of the PHY, we don't need to worry about it in legacy. Legacy advertising types are always used only on the 1 meg PHY. In the case of extended, then you have other options with 2 meg PHY and coded PHY, which we'll discuss in a later masterclass. All right, so digging deeper into the packet format. So we looked at this packet format and we discussed all the different fields in here, or at least at a high level. When we go deeper into that, we'll see that part of the PDU, and this is specific for different for the types, the 3 types here. So this is specific for ADV IND, ADV non-connect IND, and ADV scan IND. For direct IND, it will not include any data. Actually, the payload in that case will be advertising address and target address, and there's no data included there. Basically, it's just used to solicit a connection from a specific device. The one that is most common, though, is going to be one of those 3. It's either connectable and scannable, or it's going to be non-connectable and scannable, or non-connectable, non-scannable. And in all these 3 cases, in all these 3 types, this is what the payload will look like. It will have an advertising address with 6 bytes, and it will have an advertising data, which can go up to 31 bytes in total. In the header is some important information. These PDU types, the 4 bits, are the ones that are defined here. So these 4 bits are defined for each of the types in this table, and that will get filled into these 4 bits. There's a reserved for future use. This is 1 bit here that's not used. There's a channel selection algorithm bit that determines, it basically indicates whether the device supports the channel selection algorithm number 2. We don't need to get into the details of that. TX address and RX address are important because the address here is 6 bytes, but there are 2 types of addresses in Bluetooth Low Energy. There's what's called the public, a random address, and there's also what's called a public address. So the public address is the one that would be registered with the IEEE, and in that case it will have a bits set here specific. I don't remember if it was 1 or 0, but 1 will be for the public address, and then 0 will be, or the other one will be for the random address. And in this case it'll be either a random static address or random resolvable address or random non-resolvable address. The RX add in this case is the one that is going to be indicating for a directed advertising. So when you have a target advertiser included in the payload instead of the advertising data in the case of the directed advertising type, then in that case this RX add would be indication or describing that address and whether it's a public or a random address. Finally, we have 8 bits or 1 byte for the length. So this indicates the length of the payload so that the receiver knows how many bytes to parse from there on. And finally, what is actually included in this advertising data? So this is up to 31 bytes, but what does the format look like? Is it just raw bytes that we can include, or does it have a defined format? Yes, it has a defined format per the spec. And this is what it looks like. So it will be a number of data structures, and it can go from 0 data structures, no data, up to the maximum that can be included in 31 bytes. But each of these data structures has a specific format. So it's kind of in an LTV format, length type value format. So it starts with a 1 byte length, and then it goes to a 1 byte type, and then the rest is going to be data. So in here, the length is actually the length of the remaining bytes after the length byte itself. And then the type is indicated and defined in the spec for specific types. So we'll take a look at those shortly. And then we have what's called the actual data or payload of the advertising data. So if you have 31 bytes and we have 31 bytes that can be fit within a single packet, and in that case, if we have an 80 structure that maybe fills in 10 bytes, we have 21 bytes left. And if we can fit more data, then we can fit more data and we can include that. However, we can't include partial data structures in the advertising data. Otherwise, the parsing will fail on the receiving end. So here's an example. We have here what's called the complete local name type. So in here, the type is going to be defined by a value. In this case, it's 09 hex, and it indicates that this is a complete local name. Now we have a length, and this is 0B, and then the remaining I decided to put in here novel bits with a space in the middle, and each of these is going to just be the ASCII equivalent for this letter or for this character, and it's included as raw bytes. So this is what a raw data or format for the actual advertising data would look like. It would start with 0B, 09, 4E, and go all the way up to here. So now we'll take a look at how we actually find these values and how we find the format that it needs to follow for anything in this part of the data structure. So there is what's called a core spec supplement, or supplement to the Bluetooth core specification. So in addition to the main core specification, which is pretty long, it's around 3,816 pages. So it's pretty long. However, the advertising data types are not defined in this, so it's much easier to find. So this is where you'll find it. It's in a spec called the supplement to the Bluetooth core, and it is available on the Bluetooth website. I'll provide links for all of these again below the video so you can refer to them yourself. In this case, I'm looking at version 12, which is the latest as of the recording of this video. And in here, if you go to the data types, definitions, and formats, you'll see this lists all the data types. Beyond that, you'll go in and you'll see all the different data types that can be included. So we have what's called service UUID. We have local name, which is what we used and what we showed here. That's the local name. There's a complete local name, a shortened local name. There's also flags. So if we look at local name, you'll see that the data type will have complete local name UTF-8s, and that consists of it will constitute the complete local name that it's being used, they're being sent. The flags is the one where I mentioned. So in this case, for example, you could include flags and a local name. So you'll have one structure for the flags, which is 3 bytes. And this is what the format looks like. It'll have the length, the type, as with any other data structure. And then in the value, it'll actually be just 1 byte as well. And this is where it defines whether it's limited discoverable versus general discoverable. So the flags are usually included in the advertising data in order to communicate these bits and these fields and properties. In addition to flags, then we can maybe look at TX power level, for example. So in this case, you can actually include a signed power level that can go from -127 to +127 dBm. And you can see there's multiple different types of advertising data types. The issue is you have to use one of these data types. But what if you find something, or you don't find any type that satisfies the requirements for your application, or that actually defines the type or data for your application? And that's where what's called the manufacturer specific data type comes in. So this is a catch-all. It's a way to send out proprietary information in any format that you choose. There is, however, one requirement for this. So instead of having just the raw data be here, they decided to include 2 bytes, or reserve 2 bytes in the beginning of this data for what's called the company identifier code. So this is a registered number that you can obtain as a Bluetooth SIG member. And again, you can, as a company, you can join the Bluetooth SIG as a member for free, as an adopter level member, and you can request a company identifier code. So you'll find that these are defined and they're specified, and they can be assigned by the Bluetooth SIG. Once you have one, you can use it then in your data. Nobody's verifying any of these though, so you can use whatever you want in the advertising data. Nobody can stop you, but it's good to have something assigned to your own company so that you can define your own format as well for the data that follows it, and be able to filter out any other devices that maybe don't follow that. So we still didn't cover where we got these values from. So we know how we get the length. We know how we get the actual value. We know the format of the value from this specification. There is a final specification that you would want to refer to called the assigned numbers document. I'll also include a link to this, and in that document, if you refer to the section 2.3 common data types, this is where you'll actually find the value that defines that type. So if I looked for complete local name, this is where I got the 09 hex from. And this is where you'll get any of these types. And if you scroll down all the way to the bottom of that table, you'll see that FF is the one that specifies the manufacturer specific data. So if we wanted to include manufacturer specific data, we would define the length for that data and define the length for everything that's included beyond that. The type will be 0xFF, and it has to be assigned that value in order for the scanner to recognize that and parse it and be able to provide it to you. So, and I think on iOS devices, it will read all this and provide you the data that comes in here, so you won't even get access to this. That's why it has to follow the actual format and the type that's specified for manufacturer specific data in order to get that information. And if it fails the parsing, then it won't even provide anything. I think on Android it does allow you to get the raw data regardless. But in that case, in the manufacturer specific data type, we'll have 0xFF here, and then you have to include the 2 byte company ID or company identifier code, and then after that you can include the raw data. So if you think about it, if you just wanted to include manufacturer specific data in your 31 bytes, 1 byte will go here, will go away, so we'll have 30 bytes left here. 1 byte will go towards the type, that's 29 bytes. 2 bytes will go towards the company ID. That's 27 bytes left for us. And that's exactly how many bytes we have left that we can include data. But 27 bytes is actually quite a lot, especially for sensor devices and for this amount of data that IoT devices are wanting to broadcast to other devices. 27 bytes, you can fit a lot in that. So you can define your own format for that 27 bytes and be able to discover it and parse it on the scanner side and extract the data that you're interested in. So just a very quick quiz kind of question, just to pique your curiosity before we get into the actual exercises. What do you think are the most common ways of identifying BLE devices, or what are different ways of identifying BLE devices? So there's Bluetooth address. So if we go back to the format, you can see that the address is included in the header or in the actual payload, as well as the header defining whether this is a public address or a random address. And so in that case, if the device, the scanner, the platform, and the stack allows you to read this, then you can identify a device by that specific address. On iOS, these are not reported back to the application. A specific UID is assigned, maybe based on a hash or something of this, and reported up to the application. And it's different on each device that is scanning, for example, so you won't be able to correlate that to the actual address across multiple devices. So in that case, you can't really rely on this being or relying on that for identifying based on what's in the payload. So because that's not reported on iOS devices. On Android, it is reported, so you can use this to identify a device. However, if we look at the spec, actually, we will see that there is a type for the Bluetooth device address, which will help us overcome this limitation in iOS devices. So we can use this type to include that, but it will take away from the 31 bytes that can be used for other things by your application. Another way of identifying is by device name. So the complete local name is actually referred to in a lot of cases as the device name because it also corresponds and usually matches something that's in the characteristics of the device once you connect. But the device name can be used to identify a device. And then you have manufacturer-specific data. That's also very commonly used for including some sort of identifier data or some sort of type that you want to include, maybe for all your different models of a specific product that you want to include. Then you can specify that and put it in the manufacturer-specific data and then be able to parse it and recognize it on the scanning side. Service UID is pretty similar. It just indicates that a device supports, so it is a type that's included in here and it's available, so you can use that. It includes a 16-bit or 32-bit or 128-bit UUID that you can include. That some of them are standardized, some can be custom, but it kind of gives the scanner an indication of a specific service that's supported by this device. And UUIDs and service UUIDs have a meaning for in the GATT when you have connections between devices. So in that case, it usually refers to something being implemented by the device. And finally, RSSI. This is not necessarily for identifying, but you could kind of use that to filter out unwanted devices. So if you, for example, have a Bluetooth low energy device and you ask the user to maybe press a button to include some sort of data in the specific data in the advertising packet, or even start the advertising packet, and then you tell them to bring it closer to your mobile phone that's running your app, then you can start kind of referring or inferring from the RSSI the devices that you're interested in. So you maybe filter by RSSI that is only higher or equals to a specific number, and then only look at those devices and present them to the user to connect to, instead of presenting hundreds of devices or tens of devices that are discovered in the whole vicinity. Okay, so it's now time to actually get down and get our hands dirty with some exercises on the Silicon Labs BG22 Explorer Kit board. All right, so here I have Silicon Labs Simplicity Studio IDE, which is used for programming and for development for their platforms. So I have a project, and I'll be providing a link to the GitHub repo where this will be hosted, so you can import it directly and not have to worry about writing this yourself. And you can use it to experiment and kind of follow along with the exercises and the demos that we're running in this masterclass. So in here, I'll just go ahead and kind of explain a little bit on how to import the project. So once you have this open, what you can do is you have Simplicity Studio downloaded, and you can do an import and MCU project. And if you have any projects already open, you'll be presented with this display. If not, then you'll be presented with a different dialog. The one that if you have something open, you want to make sure you go to more import options, and then you do existing projects into workspace. I believe this shows up automatically once you have nothing open here, so you won't have to worry about that. But in this case, you choose existing projects into workspaces, browse to the GitHub repo that I provided that you can download and clone locally. go next and just hit import, and then you'll be able to run this and compile it and then flash it to your device. So first things first, I have the development kit that is already connected to my PC here, and it is the BG22 Explorer kit. The first thing that I could do to verify that this is connected is go to the launcher perspective and make sure that you go to debug adapters. I can do a refresh. I can see that it's going to recognize my device. Just wait for a second. When it gets recognized, it's called the BGM220 Explorer Kit board. This is what it looks like. The first thing you want to do once you get your hands on that board is to go to the launcher, find it, select it, and then click on example projects and demos. First, we want to make sure that we get a bootloader on it. And in order to do that, the easiest way is to look for a specific demo, or any of these demos really that are Bluetooth Low Energy specific. So I'm going to select the one that I always select, is called Bluetooth SoC Blinky. I unclicked or untoggled example projects in order to be able to just see the demos, which makes it easier to find this, or you can do a filter on keywords. I just hit run. This won't have to compile or do anything. It'll just flash it to the device. And now I have a bootloader on the device, and I'm running a serial port terminal, and I can verify this. If I reset the board, I can see that it's printing out some debug messages. So I know that it is running correctly. Then from there, you can make sure that you have a bootloader, because these applications will not have a bootloader included. So what we want to do is do that. And then once you check out this project, you can build it and flash it directly to the device. And just one thing to keep a note of. Okay, so say I built this project and I make sure that it builds with no errors, no warnings. Once that's done, the way that you flash it is you go into binaries. You either click on the hex or the S37. I'm going to right click and go down to flash to device. Now the most important thing here is to go to advanced settings, and this I believe only needs to be done once after installation of Simplicity Studio, but it's always good to check this if you run into issues, because this really tripped me up in the beginning. But go into advanced settings and make sure that merge content selection is the option is selected. I think by default it's page erase, so that can trip you up. It'll basically, when you program this, when you flash it to your device, it will just overwrite the bootloader and it'll be gone and it won't work. So you want to make sure that you merge content, because we just flashed it with the bootloader with that demo, and I just want to reflash it or reflash the application part. So you make sure that's selected, merge content, and then you go into program, and that should work. So if I go to the serial port and I clear it, I'm going to reset the device again, and I can see that my advertising data example is now running. So let's go ahead and explain what this example does. It's pretty simple, not very long, about 190 lines of code. This was actually modified from the SoC empty example that's available, and I just added my own code to it. So just some basic structure. Usually when you start with something from an SoC empty, for example, as the foundation for your application, the only file that you have to worry about in the beginning is app.c. So once you go into app.c, this is what you'll be presented with. And here I made some modifications, but let's go through the general structure. So what you'll already have in there is what's called the app init function. So this is where once the device boots up, if you need to call some functions or APIs, you would call them in this function. The next one is app process action. So if you have something that needs to be continuously called, like in a while loop, then you would call it from this, and the stack will call this for you. And finally, the SLBT on event, that's the third function that's included. So there's not a lot to this file, this application. This will be auto-generated or auto-filled for you from the SoC empty example. And the main one that will be in there is the system boot ID event. This indicates that the stack and the radio is ready for you to handle any Bluetooth or run any Bluetooth low energy operations. And that's where you see here by starting advertising data example is already included here by logging. And then what I'm doing is I'm getting the identity address, which is actually assigned as the Bluetooth, or used, part of it is used to assign the Bluetooth address. So I'm just grabbing that and printing that out to the debug message or the debug log so I can easily find the Bluetooth address. I'm also printing the type, so this is a public device address. So I can use this, plug it into the Bluetooth sniffer software in order to filter for this device only and be able to easily find the packets from only my device. So the next thing that I'm doing in here is to create an advertiser set. So here we have to we have to specify a variable or define a variable called advertising set handle that gets passed in to here, and this is what gets used from there on to define parameters and start the advertising itself. So in here, after I do this, I'm setting the actual data, and we'll go up to the data and we'll look at it here shortly. But here I'm setting the actual advertising data. After that, I have some commented code. We'll get to that later. And then I'm setting the timing. So here I'm setting the advertising interval to 100 milliseconds. And this is not in 100 millisecond value units that is being passed in, because the API is expecting 0.625 units. So if you multiply 160 by 0.625, you'll get 100, and that's 100 milliseconds. So there's a min and there's a max. You're basically telling the controller to choose something in between the min and max, and if you don't have anything else running in your application for advertising, for example, then we could just be very stringent and call it min equals max and tell the controller to actually go with 100 milliseconds in this case. Advertising duration means, in this case, it's 0, so that means it's going to be advertising indefinitely. And then we have the maximum number of advertising events. When it's set to 0, it's also going to advertise indefinitely. Finally, I'm just starting the advertising, and here I'm choosing the type. So let's go back up and look at the advertising data itself. So here I'm defining a couple of things, a couple of macros, one for the actual value of the complete local name that I'm using, that I'm including in the data, as well as the length. I'm calculating it here based on this. There's a null character that's being returned by size of, so a null terminator. So in that case, I'm just subtracting 1 to get the actual value, which ends up being 4, 5, 6, 7, 8, 9, 10. So 10 bytes here. And then I'm defining the actual data structure. So again, this will correspond to what we saw here. So we'll have a length, a type, and actual values. And we'll repeat that for the number of structures that we have that we want to include in the advertising data. So in here we have length, type, value for flags, and I'm including the flags in this case. And then I'm including the device name, length, type, and value. And in this case, it's an array of characters, or uint8. So this is the defined structure, but then I go and create a const that actually specifies and assigns the values to the fields within that struct. So I'm going with length equals 2 because this has 2 bytes after it. The type is 0, 1. So this is flags. If I go and refer back to the specification and look at flags, what does this mean? So again, the 0, 1 is coming from the assigned numbers document. And if I scroll up here, you'll see that flags is assigned the value 0, 1. 06 is coming from here. So if I look at here, 06 is going to be bit 1 and bit 2 assigned to 1, because this is a bit value or bit fields. So it'll have bit 1 being set and bit 2 being set, and that will combined, it will equal the value of 6 in hex or 6. And in this case, it means it's general discoverable mode, and it says that BR, EDR, or Bluetooth Classic is not supported. After that, I have the device name length. So this is going to match exactly what we had in here. So I have 0b, which is automatically calculated via that macro that I have that uses size of. And then I have 09, and then I fill it out with the actual value. So in here, I have 09, and then I fill it out with just the value that's you can get from the macro up here. And that's how simple it is. So we defined the struct, which defined the format, the variables, the fields, and then we actually assign the values. And this is what we'll be using down below when we set the advertising data. So if you see here, I'm setting the advertising data. I have to use this legacy advertiser set data. There is an extended advertiser set data, which is meant for extended advertising. In our case, we are using legacy. So we are just passing in the handle, which we set here, or we passed in here, and we got the value. This is what's used below that, beyond that, in order to refer to that specific advertising set. Then I'm setting the actual advertising data versus scan response, which we'll look at later. And then we'll just pass in the size and the actual data. And that's it. That's what sets that data. Next here, and after that, so we're done with that, I have something to define the scan response data, which we'll look at shortly when we start looking at scannable types. So the first thing that I want to look at below then is where I assign the type. So in this case, I'm assigning it to what's called non-connectable. And I can command on Mac or control click on this, and it'll open the definition in the API, in the header file. And this we can refer to this here and see what type of enum values that we have available for the different types and some description. So non-connectable is actually non-connectable and non-scannable, and we know it's undirected because the directed is only here. Where is the directed? I think it's not defined in this one, but in this case we have the non-connectable, we have connectable scannable, and we have scannable non-connectable. So there's a non-connectable non-scannable, there's a non-connectable scannable, and there's a connectable scannable. And these are the ones that are available for legacy here. This one in here is connectable non-scannable, and again we said we don't have that available in legacy, and you can see here that this is used in extended advertising PDUs. So these are the three that we are going to test out, and the first one we're testing out is non-connectable non-scannable. So that's why since it's non-scannable, I don't have this commented or uncommented yet, the scan response data, so we're only going to see one packet sent on the advertising channels, and we won't see an additional data that comes in. It'll be the same exact packet that's sent on 37, 38, and 39, and then after the at the next advertising event, it'll do the same thing over and over again. So we won't see any scan responses or scan requests, and we can't see any connections because in this case it's non-connectable. So I'm already running. What I want to do now is actually go to the sniffer software. So I am using this Minimorph, the RF Creations Minimorph Bluetooth sniffer, and this is a commercial sniffer. It supports both classic and LE and runs the software Blue Spy on both on iOS, on Mac OS, Windows, and Linux. So it is cross-platform, and I'm running it on a Mac here, and I'm going to start a new capture. So I want to first connect to it. Once it's connected, I'm going to start new capture. I don't care about saving this old one, and I'm going to make sure, go into filter devices, and I see I already have this in here, so I'm already have it selected, so it's actually showing me only the packets from my device. And you can see here it's device filter 1, which matches the one here. If I wanted to see everything, I can just do no device filtering, and then you'll get overwhelmed with all these devices. As you can see here, I have so far around 62 devices just in the area, going down to like minus 87 dBm. But I only care about my device for this exercise, so that's what I have selected here. And now I can see the actual type. So you can see here, I can click on any of these. I can see the channel, the LE channel index. So in this case, it is being sent on 38, 39, 38, 39, 37, 39, 37, 38. So you can see the sequence is not always the same. So here I can see now I can switch to a different grouping. So let's see logical, for example, or let's go to application level. Application level, this will group everything into a single advertising or single grouping, and it'll just tell us the duration of that. If I go to transaction, that's where I can see them grouped by advertising event. So in this case, let's take a look at one of these, for example, and you can see they all match the type that we referred to here in the spec. So in here, ADV non-connect IND, that's non-connectable, non-scannable, undirected, and that's the type that we used in the Silicon Labs API. And you can see it matches here, and we see that there are 3 packets. So if I expand this, I can see the first one got sent on 37, 39, 38. The next event, it was 37, 38, 39. So you can see it's randomly selecting this in order to make it harder for collisions to happen across devices. So this will contain the data that we want. So how do we actually see the data? You can see here it's already displaying that device name, but I can select any of these packets, and you can see here there are no scan requests coming in, there's no connection indication packets coming in, and that's because it's non-connectable and non-scannable. So I select one of these, I can go to what's called details, and now here I can actually see the advertising payload. So in here I have the advertising address. So if we go back to that here, you can see that the payload includes the address and the advertising data itself. So that's the address, and then the advertising data have is 15 bytes, and that matches what we were expecting there. So if we go back to Simplicity Studio and I look at this, we have 3 bytes for the flags, and then we have 10 bytes for the name, 11, 12, so 12 and 3 is 15, and that's what we're expecting to see in the scanner, in the sniffer. So in here, 15 bytes, you have the length, that's 2, matches what we have, the flags. So the first thing we have is the flags. So you can see here, gap, flags, and then the item 2 is complete local name. So it's already parsed that for us. I can see the length, I can see the type, I can see the individual flags being set here. And then if I close this, for example, and I go to item 2, I can see the local name, I can see the length, which is 11, the type, which is 09, and then the actual local name, novel bits. So in here, it's parsed that and it shows it to me in a human user-friendly format. But if I really wanted to look at the byte level, I can just go here. So I can select one of these and I can see the corresponding byte being selected in this case. So that's for non-connectable indication. So if I ran a scanner on the phone, for example, you can run the Simplicity Connect app on Android or iOS, and you can try to discover your device. You'll see novel bits, for example, show up, and it won't have the connect button there because it's non-connectable. So now let's go to the second one, and let's go and do a scannable one. So I'm going to uncomment this part out. I already have it filled. So in here, I'm using the manufacturer specific data. And if you recall, the type is 0xFF, that's the value. And then we had what's called the company ID. And in this case, I'm using my own company ID because NovelBits is a Bluetooth SIG member and I had requested a company ID. If I go to a assigned numbers document, I can actually find the company IDs in here. I can look them up by name. If I search, go down to N, and look for novel bits, I'll see that it should be 08D3. And it could have just done a search, but let's move on with it. And there's novel bits, 08D3. So that matches what I have in here. However, in this case, because this is 2 bytes in value, this has to be stored in or sent in little endian format, so it'll have the 2 bytes flipped. Now on the cipher side, you'll see that it is actually parsing it to novel bits, and it knows that because of the database. But if I do look, or not here yet, but we haven't looked at it yet. But we'll see once we capture this, we'll see that it discovers, it recognizes this as novel bits, and it displays that in the parser part of the details of the packet. The next thing in here, I just included some random values, basically going from 01 all the way to 1B. And then in here, this sets the advertising data. And in order to set the response packet, I have to uncomment this part out. And then what I'm going to do here is I'm just going to comment this part that sets the non-connectable, non-scannable, and I'm going to uncomment this part, which uses a scannable, non-connectable. So this is non-connectable, but it is scannable. I just saved that file and I can build it. Once it builds, I can go ahead and select the S37 file under binaries and go program it. I can verify that it's working correctly by looking at the serial. I just restarted, so in here I'm using a program called Serial that's available on macOS, and I can see here that I'm setting scan response data now, and now I can switch to Blue Spy. So let me do a new capture so we can verify that now we're not using the non-connectable, non-scannable. So now we are actually seeing a bunch of scannable INDs and scannable scan responses. So ADV scan IND corresponds to the one that's scannable but non-connectable. So here you can see scannable undirected event is ADV scan IND. So that is the type that we're seeing here. But we're also seeing some scan responses and scan requests. So sometimes you won't see the scan response if the sniffer is far away from the device that actually sent the scan request. So you'll see the scan response only, and you won't see the scan request. But in a lot of cases, you will see both, and that's what you see here. And you can see here, if I select this and I go to the payload, this one is just the scan request. It doesn't really have anything. It'll just have the advertiser address and the scanner address. And then the scan response, you can see here, it recognizes this as novel bits. But if I select it, you can see it's reversed, just like we entered it as D308 instead of 08D3, which is what's defined in assigned numbers. And then after that, you can see the values going from 01 to 1B correctly as we thought it would be, as we set it in the packet. So that showcases how scan requests and scan responses. The only one thing that I want to show here in addition for scan requests and scan responses is the timing of when this happens. So if you look at here, scan requests and scan response, in this case, you can see it happened on exactly the same channel. So what is required by the advertiser is that once it sends any of these scannable or connectable, it will have to stay on the same channel for another 150 microseconds after it finishes sending out this packet. And then that is required so that it can listen to any potential scan requests or connection requests that are coming from devices that are scanning. And that's in the case of a connectable or a scannable. So in this case, it's a scannable one. It's non-connectable, but it's scannable. So it is required to do that. And we can verify the 150 microseconds in the timing diagram or timing view down here. So I'm going to select this packet. And that's the last packet that got sent before the scan request. So I have it here, and I can measure the time. So I can take it from the end of this to the beginning of this. And actually, this is not the scan request because that's not being shown here because I'm filtering only for my device. And remember, scan request is coming from the scanner device. So how I can do this is I can right select and I can add that device to filter. And in that case, now it shows a second row in here, and you'll see that it's showing the scan request. So I see the scan indication, and then I see the scan request right after it. I can zoom in a little bit more to see that in closer detail. So in here, this is the scan indication. This is the scan request, and I can zoom in a little bit more and perform the timing measurement. So let me do timing between the end of this and the end of this. And let's see. How do we do that? I'm going to clear all the cursors for now. Let me measure from here all the way to here. And you can see here, you might not see it very closely, but it's around 150 microseconds. So it received the scan request, and now the scanner is also has to stay awake for, or has to wake up after 150 microseconds after this scan request. So scan request comes in. Where was that packet? Oops, we missed it. Okay, so scan request comes in from the scanner, and so after that, the scan response has to happen within 150 microseconds after that. And that's what you can see here in the timing as well. The text might be a little bit small, but it's 150 microseconds, 149 point something in this case. So it is following the spec in this case, and it is staying awake for 150 microseconds for the scanner to send the scan request. And then the scan request, after the scanner sends that, it has to be awake. It has to wake up or listen on that same channel 38 for after 150 microseconds to receive the scan response. And after that, you'll see that it goes to the different channels after that. So that's all I wanted to cover for non-connectable. And the final one I wanted to cover is just connectable. And again, if you recall, with connectable, it has to be scannable, or it is scannable. You don't have to include something in the scan response, but I'll just keep it the way it is and include something. I'm just going to select the connectable scannable instead and try it out. So that's all I have to change, just the type. I'm going to build this. And now I'm going to flash it. And then we'll take a look in the sniffer software in Blue Spy and verify that we are sending connectable. So if I go back to here, the connectable scannable is supposed to show up as ADV IND. Let me start a new capture, and I'm going to remove that second device because I just want my devices. And now you can see it's all ADV IND packets. So I can see here there's 139, 37, 38. But at the same time, because it's also scannable, you'll see that it's getting a lot of scan requests and sending back scan responses as well. And finally, if I really wanted to see what a connection would look like, I can actually do this from my phone. I'm going to run Simplicity Connect. I'm going to do a scan. I can sort by RSSI in order to find the device, and I'll just move the phone closer to my development kit to actually see it. I can see it now, and if I hit connect, you'll see that in here, and you'll see that it went into connectable mode. So it's now in a connection, and you no longer see any advertising packets. So in order to see that, you can look at that last one. You'll see that there's a connect indication packet, and we can look at the details in here. We won't cover this here, but just a high-level overview. This is the payload of the connect IND. It'll include a bunch of data, including the access address. Remember, the access address is not fixed for connections. It is fixed for advertising packets. So if I go back to the advertising packets, I'll see that the access address is always going to be the same. So if I open this up and I take a look at each of these, I can look at the access address. It is going to be, where is it? Access address. And it automatically verifies that this is advertising access address. So this will be the same for all of them. It's going to be 8E89BED6, and that's defined in the spec. However, for connections, it's going to identify the connection between these two devices, so it'll be assigned randomly by the device that initiates the connection. And there's a bunch of other values that define the connection parameters. So that's all I wanted to cover for legacy. I mean, this covers everything you really need to know about legacy advertising. In the next parts, we will be getting deeper and going into extended advertising, which was included or introduced in Bluetooth 5.0 version 5.0. It is still optional, and it's not backward compatible, so it is optional to implement any Bluetooth device, even with 5.0 or later. Then we get into periodic advertising, another type, and also periodic advertising with responses. Hope you found this helpful. If so, hit the like button, share it with others, please, and subscribe to the channel for part 2 and upcoming parts as well. Thank you for watching.